Okay, perhaps we have to start. Let me start with some overview over here. And I would like to phrase this set of issues that we will discuss today in terms of how much information is physical. Starting with the, I order this in a set of 4, but let me start with the extreme cases, the vector potential A and the magnetic field B. Now, I will say that A contains more information than B. What's higher contains more information. Now, when I say information, I don't necessarily mean physical information, right? The extra information may not be physical, and that is part of the issue. When I say A contains more information than B, I mean the following. If I tell you A, then you know what B is, right? I give you A, you take the curl. That's unique. But going backwards is not unique. If I tell you B, then you cannot determine A uniquely. There are different A's, say A1, A2, that correspond to the same B. So if I tell you B, you need some extra information to decide whether it is A1 or A2 or A3, all right? So you need some extra information. Now, that extra information could be just mathematical information. It may carry no physical significance, okay? So in that sense, A contains more information than B. And in the ordinary situation that you are familiar with, that extra information contains no physics. That is, there is no measurement which can tell you anything about that extra information. That extra information is purely mathematics, purely convention. All right? So distinguish between two concepts. What has more information and whether that extra information is physical or purely convention. Now, A actually contains more information than this closed-loop integral, because if I tell you what A is, you can certainly do the integral. But if I only tell you the integral, that would not determine A in reverse, because if A is changed by a gradient, the closed-loop integral of a gradient is 0. Right? Now, this, of course, contains actually, in your normal thinking, this contains the same information as B. Because if, by Stokes' theorem, that integral is equal to the surface integral of B. So if you tell me B, I can get that integral. Right? But in cases where the topology is not simply connected, the two may not be exactly the same. And I will come to that in examples. This actually contains more information than this. This is the integral multiplied by E over H bar, but modulo 2 pi. Okay? So if I tell you this, well, this is, of course, contains the same information as this. That doesn't matter. If I tell you this is, say, 2 pi plus 0.1, then that tells you this is 0.1, right? Now, mod 2 pi means you just throw away any multiples of 2 pi. But the reverse is not true. If I tell you this is 0.1, then this could be 0.1, or 0.1 plus 2 pi, or 0.1 plus 4 pi. So this has less information. Now, again, there is an issue about connectivity, because if this applies to all loops which can be distorted to a point, right? Suppose I have a loop here, and I can smoothly distort it to a tiny little loop and ultimately a point. Then, of course, as I distort the n pi, the 2n pi, the n cannot change discontinuously. And when I distort to a tiny loop, provided there are no singularities, the loop integral has to be 0, right? Because it's A integrated over a tiny loop has to be 0. So if you pin down the value of n in that case, the value of n has to be 0, right? It can only be, a tiny number, not a tiny number plus 2 pi, okay? Then as you continuously distort, that 2n pi, that n, must remain constant, okay? It gradually changes from a small number, like 0.01 to 0.02, 0.03. Cannot change from 0.01 to 2 pi plus 0.01 suddenly, okay? So for loops that can be continuously distorted to a point, whether you take modulus is really irrelevant. You can't get extra degrees of freedom by taking modulus. and something interesting happens only for topologies where you cannot shrink to a point. And these will be the examples we discuss. And I will discuss this set of issues with respect to two problems that are physical. One is the Aharonov-Bohm effect, which I will start on immediately, which tells you that it's not just B, but this integral that is relevant. Okay? Just telling you B is not enough. You have to go more than B. Then I will talk about magnetic monopoles. The strength of a magnetic monopole I will call G. If you believe, as I said last time, that all you need to talk about is the magnetic field, then any G is allowed. Just like divergence rho, E is equal to rho, the charge density, then you write divergence B is rho prime, the magnetic charge density. And magnetic charges can be G times a delta function. That's a point magnetic charge or magnetic monopole. And if you just write down Maxwell's equations in terms of E and B and assume that the magnetic charge density is a sum of delta functions, then any strength is allowed for the delta function. But if you believe that A is what is required, that all of A is physical, then no magnetic monopoles are allowed. Okay? And that is easy to understand, because if A is physical, then B equals curl A, then divergence of B must be equal to 0, divergence of a curl. So no magnetic monopole is allowed. But the actual situation is actually halfway in between. And that is very interesting, that only some magnetic monopole strengths are allowed. Okay? Not all possible ones, not all ruled out, but some values are allowed in quantized units. And this was first discovered by Dirac in the 1930s. Okay? And this relates to the fact that what is relevant is this guy, right? Not B. B carries too little information, that carries too much information, this carries just the right amount of information. And if you insist on that right amount of information, you find what is the quantization unit for magnetic monopoles. That's a very interesting result. Okay? And this will be one of the key results in this lecture. Right? Actually, there are three possible derivations of this result. The Dirac derivation, which is actually very complicated. I will mention it very briefly. Then there is the derivation by Professor Yang, which I will present. And there is also a simple derivation that Professor Lai and I gave. In fact, last time Professor Yang gave this such a course, almost 20 years ago, I was sitting in the audience, and then Professor Lai and myself later wrote up a short paper giving a very simple derivation. The last one I actually assigned as a problem. But if we have time, I will, since you may not have time to do all the problems, if I have time today, I will just take you through that problem. It's so simple that even an undergraduate can do it step by step. Okay? Don't even have to learn about vector potentials. Actually, that's trying to get the same result without mentioning vector potentials. Okay. So in this lecture, we'll talk about actually three physical concepts, three physical phenomena, and then one idea in mathematics. The Aharonov-Bohm effect, then flux quantization in superconductors, then magnetic monopoles, and then very briefly about the mathematical idea of a fiber bundle. Okay. So going back, if I look in classical physics only, then really the only thing relevant is the magnetic field, B. And A is just a computational device. If you are doing classical physics only, you can just drop all the A's, never talk about A's. Just write the Maxwell's equations in terms of B, okay? And it may be a little bit more difficult to solve, but that's, you have a sufficiently good computers, you can discretize, you can solve it, no problem. You don't even have to talk about A, okay? So, but in quantum mechanics, A actually appears, and let me remind you, it is because in quantum mechanics, this guy appears, and this is actually this guy appears, okay? You have to look at this operator. And so without A, you cannot even write down Schrödinger's equation. So you have to have A. But A, of course, can be changed together with a phase rotation on the wave function. All right? That's the gauge transformation. Now, Aharonov and Bohm in, I think, the late 1950s, this was quite some time ago, these are two theorists, showed the following. Because normally you think that A is really unphysical beyond A. And they showed that some aspects of A, and to be precise, it is those aspects of A that do not affect B, okay, can actually be measured. And to put it even more precisely in operational terms, they proposed an experimental situation where you have, let's say, an electron. Of course, this is quantum mechanics, so it's an electron wave function, all right? An electron that propagates only in those areas of space where B is exactly equal to 0. So in classical physics, nothing ever happens, right? Well, electric field is always 0 in this experiment, all right? So the particle never experiences an electric field, never experiences a magnetic field. So in classical physics, nothing happens. Trivial, like free space, right? But Aharonov and Bohm proposed an experiment where you can do such an experiment. A charged particle goes through space in regions never touching any magnetic field. But there is an effect, and that effect depends on the value of A. Okay? Now let's see how that goes. Let me start by something very simple, a two-slit experiment. You learn about two-slit experiments even in high school, probably at least in Hong Kong high school. There's a syllabus where you do experiments with ripple tanks, right? You put some water in a tank and shake it, and you have a barrier with two holes, and you have interference, right? And you have done the analog of this with microwaves, with optics, using lasers, double slit, you know, that kind of thing, right? And the whole idea always is that you have one source, or for that matter, two coherent sources. They have to be coherent. But to be simple, one source, and the wave actually propagates along two paths. And so when you detect the wave, say, on the screen on the right, you will observe interference. That, of course, also happens with electrons, because electrons are also waves, where the wavelength is given by de Broglie, right? So this idea applies to everything, to water waves, to sound waves, to light, to electrons. It's just that there's always interference. Okay? And the idea that even electron waves can interfere is key to the development of quantum mechanics, because quantum mechanics depends on a complex wave function, and interference is a key idea. All right? So that's simple. So let's imagine we do an experiment with electrons. So I send electrons on two possible paths, and they come back on the screen. What sort of interference pattern would I observe? Well, the wave function would be the sum of two wave functions, depending on the two paths. That's what happens in interference, right? Two amplitudes add. And each amplitude is just a phase, e to the I phi. Let's assume they have the same magnitude. Okay? So two holes are the same size. And interference depends on the difference between the two phases. And the difference of the two phases depends on the difference in the path. So if one path and another path have a length difference delta L, right? Delta L would be 0, say at the midpoint. Say up here, the first path will be shorter, the second path will be longer. So there will be a delta L. If delta L is equal to the wavelength, then there will be a 2 pi difference in the phase. All right? So the phase is 2 pi times the number of wavelengths that are different. And of course, 2 pi over lambda is just the wave number. So the phase difference is k times the path difference. K is the wave number. And depending on delta phi, you will have either constructive interference, if delta phi is 0 or 2 pi and so on. The two terms have the same sign. And you would have destructive interference if this is pi, 3 pi, and so on. Right? So this is something you learn basically even in high school. Okay. Now let's put that somewhat more formally in terms of the Schrödinger equation. Now I write, because there is no potential energy, so I write the Schrödinger equation in this form. If you put the h bar square over 2m on that side is the usual Schrödinger equation, all right? So h bar square over 2m, this is just the momentum square, right? P squared, acting on psi is equal to E psi. Is this okay? This is just a Schrödinger equation without a potential energy, and I just shove some constants to the other side. And this bunch of constants is actually k squared, where k is the wave number, because 2me is actually the momentum p squared. Okay? So this is p squared over h bar squared, so it is k squared, wave number squared. Now I assume psi is equal to, can be written as e to the I phi, then actually this equation, you can heuristically just take the square root of this equation. You see, this says taking the gradient twice, or I gradient twice, gives you k twice. So the square root of this equation just tells you if you take the gradient once, that should give you 1 power of k. Okay? You can work out the phases yourself. So let me perhaps do it backwards. If psi is equal to e to the I phi, and gradient of psi is k, just gives you a factor of k, then this psi satisfies this equation. Is that okay? So let me just write that out a little bit. If you satisfy this equation, then what happens to I gradient of psi? This would be I gradient of e to the I phi would be equal to minus gradient phi e to the I phi. Okay? And by this equation would be minus k psi. Okay? So if the phase phi satisfies this equation, then each factor of I gradient, this should really be minus I gradient, doesn't matter. Each factor of I gradient would just pull out a factor of k. So doing it twice would give you a factor of k squared. All right? So that essentially just take the square root of the top equation, because if I take the square root of the top equation, that says I or minus I gradient on psi is equal to k psi. Okay? And the solution of this is psi is equal to e to the I phi, gradient phi is equal to minus k. Okay. Right. So if the gradient of phi is k times, oh sorry, this is wrong. There should be no phi here. No phi here. Okay? Gradient of phi is just k, not k times phi itself. Okay? So can you correct that? So gradient of phi is just minus k, no phi. So if gradient is just k, then of course the phase is just the integral of k and just k dot r, right? So if phi is k dot r, then gradient of phi is just k. Okay? This is just a complicated way of saying that the solution to the Schrödinger equation is just a plain wave, e to the I k dot r. Okay? Right. But that's just, so this phase I call the phase due to the path. All right. That slightly more rather complicated way of stating a well-known result is just to pave the way for the following situation now. I still do this experiment, but I put a solenoid in the position shown. So there is a solenoid perpendicular to the page. Okay? So there is a magnetic field pointing, say, out of the page in the red area, and only in the red area. Okay? So you have a long solenoid in which the magnetic field goes like this, and you arrange it so that the B field does not leak outside the solenoid. So the B field exists only in the red area, and the electrons goes around. So in this situation, the electron never experiences a magnetic field. Okay? You can arrange it so that the electron does not go into the red portion. Electron never experiences a field. Classically, obviously, absolutely no effect. All right? So let's see how this goes. Now, along the path of the electron, along the two black arrows, there is no B. B is equal to 0. But A is not equal to 0. Okay, let's see how that goes about. Now, by the way, I probably again goofed some minus signs, but in the end it doesn't matter. Now the equation is P minus EA squared is K squared. Okay, because Schrodinger's equation now looks like this. Minus I h bar gradient minus EA squared. This is P squared. Now looks like this, all right? Because when you describe the presence of a magnetic field, you have to use this Schrödinger equation with A. That's P minus EA squared over 2m is the magnetic field. So I just move the 2m over, divide by h bar, and so on. That gives me the first equation. I write psi as a phase. Then what? This is again same mistake here. There should be no phi here, all right? There should be no phi here. So now, well, let me take the square root of this equation. So let me do the following. Let me get the minus signs right this time. Minus I gradient minus E over h bar A square acting on psi is K square psi. Okay? Like before, I just take the gradient. So that says minus I gradient psi minus E over h bar. I just take the square root. All right? If I do it once, if I get this, then I do it twice, I get 2 powers of k. So if I take psi is equal to e to the I phi, then what I need is minus I have gradient of phi minus E over h bar A is equal to k. All right? Yeah, because everything is multiplied back by psi. Is that okay? So if I take the gradient of e to the I phi, I get gradient phi times e to the I phi back. Okay? So I now kill the psi. So what does that tell me? If gradient phi is equal to this, then phi is equal to the integral of k, and then there could be a, depending on the plus or minus, doesn't really matter. Is equal to this integral, okay? And I probably got that sign wrong, but it doesn't matter for this application. So the first term, the k, gives me k dot r. It's a constant. The line integral is trivial. Then the other terms gives me e over h bar a dr along the path. So I write this as the sum of two things. This is the original thing due to the path length. This is the phase due to a. All right? So forget about the mathematics for a moment. That just says as the electron goes along, say, this path, along the path, B is equal to 0, but A is not equal to 0. So the phase of the wave function increases along the path. One is by an amount due to the path length, k dot r, the usual one. So it increases by 2 pi for every wavelength. Right? But there is another phase given by the integral of a dot dr along this line with this factor e over h bar. Okay? There's an extra phase. And the extra phase depends on the value of a along the path. It does not depend on the value of b. So I'll skip this one. So now let me look at this interference between the two paths. So as before, I have the sum of the two amplitudes. The phase along any path, 1 or 2, is the one due to path, which is k dot r, plus a term which is the integral of this along the path. Okay? But interference depends on the difference between these two phases. What is the difference? Well, first of all, there is a difference due to the path. That is the same whether or not there is a magnetic field, right? That just depends on the position where you observe. Plus the difference between two of these things. That is the difference between the integral along here and the integral along here. So it is the integral along the top line minus the integral along the bottom line, right? Which is the integral going around this closed loop. Okay? So the difference between two such integrals along line 1 and line 2 is equal to the integral going around the line like this. This is closed loop. So that is the closed loop. Okay? So the the phase difference contains a term which depends only on the position of the observation point. The same when B is equal to 0. Plus another part which is given by the loop integral of A. Now, the loop integral of A is just equal to the total flux in the solenoid. It's not 0. Okay? So if I can change the magnetic flux. Imagine it's a solenoid, and I can, say, change the current through the solenoid. All right, so I increase the current. Then as I change the current, I dial up the current, the second term changes. If the second term changes, the phase difference changes, and I can tune the interference pattern, right? So as it gradually changes, imagine the screen, there is an interference pattern of bright and dark fringes. As I increase the magnetic field, the second term increases, then the whole pattern shifts up and down as I change B. Okay? So I can shift the physical result by changing B, even though the electron never experiences any B field. It only experiences A. Is that all right? So this was the idea proposed by Aharonov and Bohm. So this is the phase difference is equal to the path due to the path, plus a term depending on the magnetic flux. This is the magnetic flux, okay? This loop integral is the magnetic flux. So the interference pattern shifts as the flux changes. And even though the electron never experiences a B field. This paper was published by Aharonov and Bohm in 1959, a very famous paper. Initially, it did not attract a whole lot of attention because this experiment is actually very difficult to do. And people thought about it only as a curiosity. Some people believed it, some people did not, and it sort of, just lingered. Nobody paid too much attention. Until this whole idea of gauge theories was realized to be very important in the 1970s. When you talk about gauge theories, the idea that we introduced last time of a private vector space, that is the key idea to gauge theories, right? When you have private vector spaces, then what is the status of the connection 1 form as something that relates one private vector space to another private vector space? All those ideas people in the 1970s realized was actually conceptually very important. So the debate on whether Aharonov-Bohm effect is real heated up in the 1970s, and people started to do experiments. And the definitive experiment was not completed until 1986, 20 years ago, by a Japanese group, Tonomura, in, I think, Hitachi Lab. So this is evidence for the AB effect. AB is Aharonov-Bohm, with magnetic field completely shielded from electron wave. Okay? Now, why is this difficult? And this relates to the second topic I want to talk about. In a solenoid, when you first study it in first year or high school, you say all the magnetic field is inside the solenoid, and there is no magnetic field outside the solenoid, right? That is only an approximation. It's not strictly true, right? There will always be some leakage of magnetic fields. Suppose you have a coil like this. right? That is your coil. And normally you say that the flux lines go like this, right? But actually, some flux lines will do this, okay? Right? And a few may even do this. Okay? If you have a good solenoid, and if I draw this quantitatively, there may be 1 million lines going this way and 1 or 2 lines going this way. So the leakage may be 1 part in a million or whatever. So there will always be some small leakage. If you have some small leakage and you do this experiment, people are not going to be convinced, right? Because they will say, hey, the electrons actually experience a tiny bit of B. So the interference effect may be just due to that tiny bit of B rather than B equal to 0 and no A. So although the concept is easy to explain, doing the experiment is actually rather tricky. You really have to get rid of all the B's on the outside, and that requires superconductors. Okay, so I will actually talk about this later. But anyway, we derived this result, that the phase difference due to the magnetic field is E over h bar times the magnetic flux. And people in this business tend to write in terms of h rather than h bar. So I write this as 2 pi E h, right? So I write h bar as h over 2 pi times the magnetic flux. Now it turns out if I use a superconductor arrangement, the magnetic flux is quantized in units of h over 2e, and this I will derive later. The magnetic flux that you can have, not with a conventional solenoid, but with a superconductor, right, is integer times h over 2e. So if you do that arrangement, then the phase would be n times pi. Notice this 2, so it is pi. So if I change the flux by 1 unit, I shift the interference pattern by half a fringe. That is, a maximum becomes a minimum, and a minimum becomes a maximum. Okay? Now, if it's 2 pi, then you won't see anything. Okay? So if you do the magnetic field using superconducting fluxoids, then you can change the flux by discrete units, and each unit that you change will shift it exactly by half a fringe, all right? Maximum to minimum, and that's detectable. And that was what Aharonov showed in that experiment. He actually showed 2 very clean pictures. One picture like this with the fringes, one picture like this, just staggered by half a unit, right? So go and take a look at his paper, and that convinced everybody. 2 actual pictures taken of the fringe pattern, shifting by half a unit as he changed by 1 flux unit. So the conceptual importance, of course, it tells you that the loop integral is important. And in this case, it is because your loop cannot be shrunk to a point. Okay, that's very important because I'm talking about this kind of loop. And all my discussion assume that the electron never touches the B field, so I cannot shrink this set of black lines to a point, right? Because I am excluding the red portion. So there is a topological non-triviality. So that gets us one step along the question of what is the right amount of information, namely that B is not quite enough, because in this experiment, B is equal to 0, in the sense that B is 0 at the position of the electron, right? The electron always experiences B equal to 0, but there is still an effect. A is obviously too much, because I can do this kind of a transformation on A, it should have no effect. And as far as this experiment goes, this loop integral is just right. I have to tell you the value of this loop integral for every loop. That determines the result. Okay? So there are actually 2 kinds of loops in this experiment. One is this kind of loop. This kind of loop can be shrunk to a point, right? Okay? And that is the same as, therefore, the information in this kind of loop is the same as the information in infinitesimal loops, right? Because if I tell you the information for every tiny little loop, I just build it up, then it's the information for this loop. And that is just like the local B field, okay? Because the integral over a tiny loop is just the value of B times the area. So for these simple loops, the information is exactly the same as the magnetic field. No more, no less. Because these simple loops can be made up of infinitesimal loops, and infinitesimal loops reduced to B fields. That's the usual argument you are familiar with. Right? But there is a non-trivial loop, which is topologically non-trivial, namely this kind of loop. This loop cannot be reduced to infinitesimal small loops without crossing some forbidden boundaries. All right? You cannot shrink this to a point. Even if I tell you the value of every such small loop, that will never tell you the integral over the whole thing. Okay? So it is because certain loops cannot be shrunk to a point that there is a difference between giving you all loop integrals and just giving you B. Okay, so it's a top. So these issues very often are related also to deep topological issues. So in this interface between physics and mathematics, people are getting also interested in topological issues, so-called topological invariance and so on. That's another big topic that I won't have time to talk about. But actually, even this is a little bit too much, as I shall now come to in the next example. All right? Now, in terms of the normal situation, the normal gauge transformation is the first line. For that kind of gauge transformation, that does not affect the loop integral. Any questions so far before I come to the next topic? I encourage you to go and read the paper by Tonomura. The paper by Aharonov, you probably don't need to read because I have covered all the main ideas. Okay? But it's interesting from a historical point of view. In 1959, he had to argue all kinds of things because the statement was so shocking to say that an electron never experiences a B field can still have a changed behavior. Okay, so there were a lot of arguments, philosophical arguments about why it's possible and so on, which we now take for granted. Okay, so that's only of historical interest. In terms of the physics, everything in that paper is basically I have covered. But in terms of how you actually do the experiment, it's actually rather tricky. Right? Took Tonomura, I think, quite a number of years to get it right. You may like to read and see, how people actually do that experiment. Okay, now let me talk about flux quantization and superconductors. This is actually a topic that is taught in the theory of superconductors. Okay, but sometimes perhaps not in exactly this form. But the idea is actually in this form actually very simple. Now, suppose I have a ring. Right? The green part is a superconductor. Doesn't have to be very thick, just like a ring that you put on your finger. And you have this part you make into a superconductor. Now, if somehow you can generate a current in that superconductor, make a current flow. Now, you don't need a battery, right? Because it is a superconductor. There's no resistance. Once you start the current flowing, you just keep it there. So long as it's cold enough, it stays below the transition point. The current will just keep flowing. If there is a current going this way, you can imagine, and this is just elementary electrostatics, that there is a magnetic field through the hole. The magnetic field cannot, so think about the flux lines as crossing, as being in the hole. The flux lines cannot move through the ring because you know the Meissner effect. In a superconductor, inside a superconductor, B is equal to 0. Right? So think of the changes of the magnetic field as movements in the flux line. So the flux line cannot actually cross and come out. So there are flux lines trapped inside that hole. Okay? And my question is, can you say something about the flux lines or the flux inside that hole? Now, and here is why superconductors are important. Because the magnetic field is completely shielded. Okay? The magnetic field cannot cross and leak out because of the Meissner effect. Okay. So we have electrons in the green region. And to describe an electron, I again write it as phase. The phase, as before, takes this form. Same argument as before. Except in a superconductor, the basic object is not an electron, but an electron pair, a Cooper pair. Okay? Superconductors are superconducting because electrons form pairs. Now, the physics of that I leave aside. It's a very deep question as to why two electrons do not repel, but actually condense to form Cooper pairs. That's a separate story. It's a non-trivial story in many particle physics. But let's accept that they form pairs. That's the only thing you need to accept. So the whole story, the whole formalism goes through as before, except that the charge becomes 2e. The wave function is not the wave function of an electron, but the wave function of the Cooper pairs. Okay? So that's where the factor 2 comes in. So the argument is the same. So I have the phase goes like this. But now imagine I go round once. The wave function, of course, has to be unique. You must have the same wave function at each point, right? So that means psi has to be unique, so e to the I phi has to be unique. But that does not mean phi has to be unique. Phi can need only, oops. What happened? Yeah. Phi only needs to be unique up to a multiple of 2 pi. I don't have to tell you what the wave function here at the point is. I can give you the phase. I don't have to tell you what the phase is at that point. I can give you a multi-valued answer. I can tell you it's either 0 or 2 pi or 4 pi, the phase. You can't force me to give you a unique answer. I don't have to. Because ultimately, the only thing that matters is the wave function, which is e to the I phase. So the phase has to be unique up to multiple of 2 pi. So this, by the way, go round once, that means this is a loop integral, right? This is a closed loop integral. So that means this has to be unique up to 2 pi. So if I move the h bar over 2e to over here, that means this loop integral has to be an integer multiple of this thing. Okay? If it is not an integer multiple of h over 2e, then the wave function would not be single valued, and that is not allowed. Is that okay? So that means the flux inside a superconducting ring cannot be arbitrary. Must be an integer multiple of a certain fundamental flux unit. And the fundamental flux unit is h over 2e. That is the quantization of flux for superconductors. Okay? The 2 comes about because they are Cooper pairs. So the flux in the case of a superconductor is given by this is n times the basic flux unit. The basic flux unit is h over 2e. The flux unit, the flux is this. The flux is integer multiple the phi 0, and the phase is multi-valued modulo 2 pi. The phase does not have to be single-valued. The wave function has to be single-valued. So the right amount of information is that the flux must be unique. You only need to know it modulo h over 2e. Any questions? And I have used this result in discussing the Aharonov Bohm effect, the Tonomura experiment. right? It is because of the two, that the two possible states differ by pi, okay? And if you change by one flux unit, it shifts by pi and not 2 pi. If it's 2 pi, then he won't be able to show anything. Right? So this is actually not an hypothesis, not mathematics, but actually measured in experiment by Tonomura in 1986. Right. Any questions up to this point? So all having to do, you see, with some of the ideas that we are talking about, that the vector potential is related to the phase of the quantum mechanical wave function. That's the key idea in gauge theories. And it lives in the exponential. Okay? So that's the idea of phase. So you see there's several ideas coming together. This is really quantization, right? And this is phase. It is because of quantization that the momentum operator became this. And that causes the A to sit in the exponential. And that leads to the idea of phase. Okay? And this is the whole idea of gauge theories. Everything traces back to here. Is that right? Okay. Now let me come to the idea of magnetic monopoles. All right? Before I do this, perhaps I ought to remind you a bit about the classical theory of magnetic monopoles. Now, Maxwell's equations look like this, right? Divergence E is equal to, let's say, rho, the electric charge density. I will use units where epsilon 0 is 1, right? And normally, you would say divergence B is equal to 0, okay? And you have curl, let's see, curl B, let me call that rho E, is equal to JE, right? That is the electric current. And then what? Plus the EDT. Right? That last term is the displacement current due to Maxwell. Normally, you would say curl divergence B is equal to 0, and curl E is minus dB dt. Right? That is what you learned in year 2. Is that all right? The units may look slightly unfamiliar to you. I have chosen units where epsilon 0 and mu 0 are both 1. And that is consistent with C being 1. Now, suppose there are magnetic monopoles. How would you change these equations? Well, the first thing you can guess is that you change this. There would be a density of magnetic monopoles, right? Density of magnetic charge. Obvious, right? If you add that term, what else do you think you need to do? Guess. Yeah? Huh? Curl E will change. How? Yeah, so you probably guess there is some term here related to the magnetic current. But I don't know this coefficient. Let me call that alpha. And let's try to determine that, okay? Now, mathematically, you can think of it as a symmetry between the two sides, right? So if you change sort of B to E, and E to B, and electric to magnetic, okay? It's a mathematical symmetry. In physical terms, what this term says is moving charge causes a magnetic field. It's what you learn in high school, even without this term. A moving charge causes a magnetic field, right? That's what happens with solenoids. So if there is such a term, that means a moving monopole causes an electric field. Right? So it's the analog of Ampere's law. Now, let's try to prove mathematically that there has to be such a term. It may be useful to go back and look at this equation. Now, historically, this equation on the right-hand side, people first knew about this term. And this was discovered theoretically later by Maxwell, right? This was Ampere. This was discovered by Maxwell. Because he found without this, it would be logically inconsistent. Now, here, of course, the historical situation is the reverse. This has been known since the time of Faraday. This is Faraday's law. And now we want to discover this term. And I want to show that without this term, it will be also logically inconsistent. All right? So what I'm going to do with this equation is really analogous to what Maxwell did with this equation, to show that this term must be present. Okay? The mathematics will be the same, except the order is different. Here, Maxwell showed that this term had to be present because this was already known. I will now show that this term must be present because this term is already known. The two actually come together. Now, do you remember how this came about? Why both terms would have to be present? Very simple. Let's take divergence on both sides, all right? Divergence of a curl is 0. Now I use this equation. Divergence E is equal to what? It's equal to rho, right? Divergence E is equal to rho. And this is the conservation of electric charge. If you did not have this term, you would not have this term, then that would not be the conservation of charge in dynamic situations. Right? Because this is the law that tells you charge is conserved. So very simple. The two terms have to be together in order to be consistent with the conservation of charge. Just you take the divergence, the curl has to be 0. So if you remember this much, then it is actually easy to guess it, to check, see that this is actually minus. Right? Exactly the same idea. You take the divergence. The divergence of B is rho m. So you must have a divergence of J here. Right? So not only do we see that there has to be a J term in Faraday's law, Jm term in Faraday's law, but it has to come in with a minus sign. Or in other words, same sign as this term. Right, so let me erase this. So that is Maxwell's equations if there is such a thing as a magnetic monopoles. This set of equations is perfectly consistent. Nothing wrong. If I tell you what rho E, Je, rho M, Jm are, you can solve these equations and find the result. All right? Doesn't mean you can find A. If you write this down, there will be no A, because divergence B is equal to not 0, so B cannot be written as curl A. Is that right? So this is classical. Right. So let's look at quantum mechanics. And for simplicity, let me just do the static case first. Nothing is moving. So instead of writing rho E and rho M, I write rho and rho prime. Depends on the unit. Sometimes some units you write 4 pi rather than 1. Doesn't matter for the idea. So is this possible? So let me imagine a point charge, all right, which is g times a delta function. Let me see. Yeah, if I write 4 pi there, that means the following. If divergence B, if I choose a system of units where this is 4 pi rho, and if I have, let me just, okay, and you have a point charge, all right, like in the bottom line, I integrate this over a sphere, then this is converted to a surface integral. B dot ds on the surface is equal to 4 pi times the total charge inside, which is g. All right? This is connects to the convention where this number is called g. But this is 4 pi r squared times b. So b is equal to g over r squared. Okay? So I just want to explain that the convention that if you put 4 pi here, that relates to the essentially the analog of Coulomb's law. Looks like this. It's the charge divided by r squared, period. Okay? No other constants. So is that possible? So at the classical level, it's perfectly okay, like I just showed, but you put back the 4 pi's. Or in this exercise we have done, what happens to the time-dependent equations has to be these terms. At quantum level, now there seems to be a problem. Because suppose there is a magnetic monopole, let's say sitting at the origin. And I have an electron moving around, okay? So I have an electron moving around a monopole. And I want to describe the electron quantum mechanically. Then I have to write down Schrödinger's equation. Schrödinger equation demands that I use a vector potential. When divergence B is not 0, I cannot find a vector potential. So that seems to say that there can be no monopoles, if you believe in quantum mechanics. All right? Now, this argument depends on the following fact. That I try to find a function, the vector potential, which is a function of position, A of r, which is a mapping between the base space, all possible positions, and the vector space that describes A. Right? I try to find a vector function A of r that describes this, and it's not possible. Because if I can, then curl A giving me a B, that B would have 0 divergence. So let me draw this in another way. So I'm trying to find a vector function that maps from R, the base space, to the vector space for A. Try to find such a function. It's not possible. All right? There is no A applies everywhere such that B equals curl A and divergence B is not equal to 0. That is not possible in this picture, right? Because you learn in your vector calculus that if you find a B and take curl A, then taking the divergence of that curl, you have to get 0, right? To say that this is impossible is the same as the statement that divergence of a curl is 0. Not possible. Now, we realize that that is not quite the mathematical problem we have to solve. That is the trick. The idea is that A need only be defined in private vector spaces. I don't need to find one single A valid everywhere. So for each position, I have one A, and different A's, they have to patch together. I don't have to find a single A valid over the whole space. Now, you may say, if I want to find a vector function for each position, that is pretty tough. But actually, you don't have to, as I will show just in a minute. All I need is actually divide whole space into two overlapping parts. Part A, part 1, part 2. I find an A in part 1, find an A in part 2, and make sure in the overlap region they are consistent in a certain sense. Now, of course, that changes the mathematical problem, right? I'm not asking to find one A over all space to satisfy all the conditions. I relax it a little bit. I want one solution here, one solution there, and that where they overlap, I want some consistency. That is a weaker condition. Okay? And that the reason why I can relax the condition is because of this idea that these vector functions live in private spaces. I don't need a globally defined vector potential. I only need vector potentials defined only over certain parts of space. Okay, so let's see how that goes. So let me take the base space, divide it into, let's say, two regions, which I call little a and little b. They have to overlap because I have to be able to have a description that spans from here to here. In the overlap region, I have two descriptions, right? In the overlap regions, I have two vector potentials, which I call A sub A and A sub B. They must describe the same physics. That means they have to describe the same magnetic field. So in the overlap region, the difference must be the gradient of a scalar function. They differ by a gauge transformation, right? So let's see how we can do this. So let's just look at a simple case. This simple case in statics captures all the essential ideas. You can, of course, ask a tougher question about what happens when you have one moving monopole or many moving monopoles, all right? The mathematics becomes more complicated, but none of that complication has anything to do with the key idea. Right? So the key idea, let's just discuss with one monopole that is sitting at the origin, not moving. The magnetic field, therefore, is 1 over r squared, purely radial, just like Coulomb's law. Okay? So let's see what happens. So I'm going to divide all of space into two regions, two overlapping regions. So what do I do? So I have the origin. So the monopole sits at the origin here. I take the z-axis, and I draw a cone like this, where this angle is called theta 1. And I call everything above theta 1 region little a. Okay? So it's just sort of like the northern hemisphere plus a little bit. A bit more than the northern hemisphere, from the North Pole down to the equator plus a little bit more. Okay? That part I call region little a. And the other one, which is the southern hemisphere plus a little bit, I call region little b. Is that okay? So I'm going to find a vector potential that works in region A. I'm going to find a vector potential that works in region B. Now, just to save words, I will say northern hemisphere and southern hemisphere. But in fact, I want them to overlap a little bit, all right? So I want to find one for the northern hemisphere. I want to find one for the southern hemisphere. And then I will show several things. One, I will show that the one I find for the northern hemisphere cannot be extended all the way to the southern hemisphere. Because if I can, then I would have found 1A which is global. And if I find 1A which is global, I must get into trouble with this theorem. I have 1A valid everywhere. I take B equals curl A, then divergence B must be 0. Okay? So I will show that I cannot extend the northern function all the way to the south or the southern function all the way to the north. So that's sort of a negative result. Then the positive result is that near the equator, there is an overlap region where both are possible, I have to show the two are consistent. All right? So that is the strategy. So let's see. So let me do the following. Let me consider this equation, which is just a Stokes law. That's just a mathematical equation. A dot dr around a closed loop is equal to the surface integral of the magnetic field around a latitude at angle theta. Okay? And I will assume that A, the vector potential, is entirely in the phi direction. That is always along the loop. So let me assume the vector potential, which is a vector, is always going around a latitude. All right? It is always tangential this way, around a latitude, pointing, let's say, pointing east. All right, so let's try to do this. So on the left-hand side, this integral is trivial because A and dr are parallel. As I go around the latitude, A and the infinitesimal displacement dr are parallel. So that's just the magnitude of A times the length of that circumference, which is 2 pi r sine theta. R is this line, the radius. Okay? R sine theta is the radius of that circle. Is that all right? So that is the left-hand side. R is the distance to the origin. The distance to the axis is r sine theta. Is that all right? Stokes' theorem says that line integral is equal to b dot ds, where S is any surface whose edge is this loop, right? So this is an important property of Stokes' theorem. If I do a line integral of A, the result is equal to the surface integral of B for any surface whose boundary is this loop, right? That's not unique. I could take this flat surface. I can take it bulging out like this, like a balloon. I can take it to be bulging surface in the back. It's all okay, right? Now I take it to be the surface on the sphere of radius r. Okay? But there are still two choices. There are two surfaces on the sphere of radius r whose boundary is that latitude. Either it could be the upper green cap or it could be the lower red cap, right? Do you understand what I mean? So if this line that separates red from green is that line, then this integral can be either the integral of the red cap or the integral of the green cap. Is that okay? Stokes' theorem applies in both cases, equally valid. Now, on the cap, either red or green, B is radial. So the surface and uniform are in magnitude. So that integral is actually trivial. It's just the magnitude of B, which is G over R squared, times the area. And the area is either the green area or the red area. Is this okay? Now you already see I can get two possible answers. Because I am calculating the A around this line, right? Say in the northern hemisphere, latitude 45. So that is a unique line. A has a uniform magnitude around that line. What is that magnitude? Well, it's given by this equation. Everything is unique. If I tell you it's this line, theta is unique, R is unique, G is unique, R is unique. But the area, I have two choices, either this small one or this large one. So that will give me two choices for A. Right? So let's see what happens. Let me do the upper cap. Now, I'm just going to evaluate the areas. All right? The area is always 2 pi r sine theta r d theta, right? Think about the area. This is just pure geometry. So the area is the integral of 2 pi r sine theta r d theta. Because the length around the circumference, this is 2 pi r sine theta, and this length, the width of that band is r d theta, right? So if you add that up, that is the area. You understand? That is the integrand. That is the element of area for a part of a spherical surface. For the upper cap, theta ranges from 0 to theta, right? So we go back. This line is at position theta. To calculate the area of the green cap, I do that area integral from the North Pole to theta. North Pole is theta equal to 0. So I go from 0 to theta. Do you understand? So that's the integrand is the usual thing for areas. The only tricky thing is the limits of the integral. For the upper cap, I count from the North Pole down to theta. That means I integrate from 0 to theta. That's the green cap. So let's do this integral. It is the integral of sine theta is minus cosine theta, evaluated between theta and 0. And that gives me 1 minus cosine theta. 2 pi r squared, 1 minus cosine theta. Let's check this. If I go all the way down to the South Pole, cosine theta would be minus 1. And I would get 4 pi r squared, which is correct, which is the area of the whole sphere. Okay, that checks it for the green one. Now, let's think about a little bit about signs. If I go around the loop this way, say this is the sphere, I go around the loop this way, the right-hand rule tells me that if my line integral goes this way, I calculate the surface integral with the normal this way. And that is the same direction as the magnetic field. So I get a plus sign for the integral. Now, let me do it for the lower cap. For the lower cap, I have to calculate the area for the theta integral from theta all the way to the South Pole, right? So that means, I calculate from theta, the same integral now I take from theta to pi. All right? That is the area of the South Pole. And again, the same thing, from theta to pi, you get 1 plus cosine theta. Now, never mind the overall sign outside. I will come to that in a minute. First of all, the relative plus sign inside the bracket, does that make sense? I am now integrating from the South Pole up to theta. So let me take the limit where I go all the way to the North Pole. That means theta is equal to 0. And I, again, get up to a minus sign, overall minus sign, 4 pi r squared. So that's correct. So it has to be 1 plus. Okay? But what about the overall minus sign? This means this whole expression has a minus sign. And that, of course, makes sense, because if I'm going around the loop like this, then my surface integral has to be counted this way as positive, but my B field is radially outwards. So there is a difference or a minus sign. Okay? So when I count the area, because when you do Stokes' theorem, you do the surface integral, essentially you're measuring area. Is the area positive or negative? That is a matter of sign convention. That has to be consistent. So it's overall minus times this. Is that all right? So let me do the calculation in parallel. So think of this as two halves of the page, all right? Nothing to do with each other. Do the calculation valid for the upper cap. And the answer I call A sub little a. All right? This means it is an answer for the upper cap. I integrate the upper cap. The left-hand side is 2 pi r. Where's the cursor? It's A times 2 pi r sine theta. G over r squared. This is the area of the cap we just calculated. Or maybe I just contrast the two. If I do the lowest cap, the left-hand side is the same. The right-hand side, this is a relative plus sign, and there is an overall minus. Both are possible. So let me divide through. So in the first expression, I divide by the sine theta to this side. So I have G over 1 power of R, right? R square, 1 R over here. G over R, 1 minus cosine theta over sine theta. And for this one, 1 plus cosine theta over sine theta. That's plus with the over or minus sign. So I have two possible expressions for the vector potential. Let me look at the first one. The first one I calculate from the top up. Let's look at that expression. Hey, there is a sine theta in the denominator. That looks bad at theta equal to 0. But no, that's okay, because the numerator also has a 0. 1 minus cosine theta. In fact, you can do some trick identities and cancel this, write it as half angles, right? Upstairs is sine square of theta over 2. Never mind factors of 2. Downstairs is sine theta over 2, cosine theta over 2. So you cancel the sine. You get sine theta over 2 over cosine theta over 2. And that is perfectly okay at theta equal to 0. So the first expression is perfectly okay at the North Pole. But it is singular in the South Pole. Right? If I try to extend the top solution all the way down, I get a singularity when theta is equal to pi. Why? When theta equals to pi, the numerator is finite. It's non-zero. In fact, it's 2. Right? 1 minus minus 1. But the denominator is 0. So if I try to extend the top solution to the South Pole, I get singularity. That means I cannot find a globally valid solution. For the lower solution, of course, the opposite is true. At pi, at the South Pole, everything is actually fine. You have a 0 here, you also have a 0 on top. Okay? But at the North Pole, it is singular. So if I try to extend this all the way to the North Pole, again, I get something singular. So what can you do? Any question about this? I'm trying to find a vector potential. And what I have actually found 2. But each one by itself is not globally valid. Okay? Now, there are several attitudes you can take at this point. I mean, this is just algebra, it's not important. But what attitude you take, that is a physical concept. The simplest attitude you can take, and that is what people assumed before the 1930s. Since I cannot find an A everywhere, there is no solution. Not allowed. No monopole. Okay? Simplest possible solution. Second solution, by Dirac. Now, and I'm going to just sketch the idea. So here is the monopole. Dirac says, let me just take the top solution. Gives me a singular B, right? So there is a singular A. A is singular along the string, a line that goes at theta equal to pi. I have a singularity, which he calls string. Nothing to do with string and string theory, all right? It's called a Dirac string. He says, let me relax my mathematics a little bit to allow singular vector potentials. So he wrote pages and pages of how to deal with singular magnetic potentials. But his basic trick is the following. Hey, I can do gauge transformations. But he's doing gauge transformations on something slightly dangerous, on a function which is singular. He showed that there is a class of gauge transformations that essentially shifts the string elsewhere. Okay? So if I am discussing what the electron does here, I first do a gauge transformation that moves the string over here. Then when I do it here, everything is fine. No singularities. Okay? So he fiddled around with a lot of transformations, gauge transformations, that operate not on normal regular functions, but on functions with a singularity, a string of singularities. And he showed that everything works out. But in the intermediate steps, he had to carry the string along. Okay? But in the end showed that it never had any effect. So the Dirac theory of monopoles was actually very messy. In the calculation, he had to carry the string along. And you can easily imagine that he even had to consider situations where the string of singularities is any line that comes from the origin. And he just moved it around. So a lot of singular stuff, tricky mathematics. So that is, and he proved the quantization condition for magnetic monopoles using this. All right? It's a very difficult paper to read. Not many people pay too much attention because not many people actually follow that paper. It's actually correct. He was a bit of a genius. It's technically non-trivial. So that's the second approach. Right? The first approach simply says, I give up. No global solution, not possible. No monopole. The second says, hey, I tolerate a singularity, but I show the singularity can be moved around and it's not physical. Now I come to the third attitude. The third attitude says, hey, I don't have to take the first solution all the way down or the second solution all the way up. I just take the top solution a little bit beyond the equator and the bottom solution a little bit above the equator. And all I have, I never encounter singularities. Because the top solution, I do not go to, or even anywhere near the South Pole. Okay? I can just go to, 45 degrees south. Nothing singular. The bottom solution, I only go to 45 degrees north. Nothing singular. Or even 1 degree south, 1 degree north, doesn't matter, so long as they overlap a little bit. In their respective domains of definition, there is no singularity. So instead of speaking of one singular A, which is what Dirac did, I now talk about two A's, each of which is not singular. One A here, they overlap. In their respective domains, they are not singular. All right? So that's the third attitude. Never have to talk about singularities. The cost is that instead of talking about one A, I now talk about two A's, two private vector spaces. And the cost is now I need to handle the issue of consistency in the overlap. So the only remaining issue is the consistency in the overlap. All right? So let's see what happens. In the overlap region, I have to check that these two are consistent. And let me look at the difference between these two. Now, notice, if I look at the difference, this minus this, the cosine term cancels, all right? Only the one term remains. So the difference between the two potentials is G over R 2 over sine theta E phi. The difference must have no physical meaning, right? It must be a gauge, pure gauge. Pure gauge means the difference is the gradient of a scalar potential. Okay? So is it true that this difference in the A can be written as the gradient of a potential? A gradient of a scalar. Can I do this? Okay? Now, if you can, if this statement is true, then the line integral around a loop must be 0, right? If you have a gradient, you do a line integral. It's the value at one end minus the value at the other end. If you have a closed loop, it's the value at the same point. It has to be 0. So consistency would seem to mean that the loop integral of this around a latitude in the overlap region must be 0. Okay? So let's check whether or not this is true. So I'm going to do this loop integral along a latitude at polar angle theta. Theta is now a loop in the overlap. Okay? And of course, the overlap still can have many theta values. So I want to check this. So I take a loop at polar angle theta, so that dr is just r sine theta d phi, right? That is, if I go around like this, then this section of dr is just r sine theta d phi along the phi direction. Okay? Because if I go around once, the d phi gives me 2 pi. R sine theta is just this radius. Okay, that radius is r sine theta. So this is delta A, this side of the dot. This is dr. Okay? Well, this integral is trivial because the r sine theta cancels. The d phi going around gives me 2 pi. Together with this 2 gives me 4 pi g. So if the monopole strength is g, the difference of the two A's integrated around a loop is 4 pi g. It's not 0. Whereas if it is equal to the gradient of a scalar, it would have to be 0. Monopole not allowed? No. Because, and this, if you remember the table I set out at the beginning of today, what is relevant is not the integral of a dr, because this actually sits on the exponential. So if I look at this and compare two A's, I do not need the two A's to give me the same phase. The phase can differ by 2 pi, right? If you say, if I just drop the exponential, then I would have to say the loop integral is unique. And therefore, the delta A loop integral has to be 0. Okay? If I drop the exponential and require it to be unique, then the loop integral of A for the first version, sub A, and the second version has to be the same. That means for delta A has to be 0. But now we realize a loophole, an escape. I need the weight to be 0, to be unique. So it's the exponential that needs to be unique. So it is possible for the two integrals to differ by 2 pi. If little a, the first version of the vector potential and the second version of the vector potential, when I put into that integral, differ only by 2 pi, that is allowed. They don't have to be exactly the same. They can differ by 2 pi. Or in other words, if I put, all I need is the delta A here, this integral, it need not be 0. All it needs is that this exponential is unique, 1. So that means this integral can be 2n pi. Does not need to be 0. Now, this is the important relaxation. That what matters is not just the loop integral of A, but the loop integral of A in the exponential. That gives me a little bit of room to maneuver. I can allow this to be a multiple of 2 pi. All right? Now, I have already done that integral. So this is 2n pi. I just move the e over h bar to the other side. So that delta A integral is n times this thing. But I have already done this integral just now. It is 4 pi g. All right? So 4 pi g does not need to be 0 because I allow delta A loop integral to be possibly non-zero, so long as it, in the face, it doesn't give me any trouble. Now, just jump back. Normally, you would say, if you have two A's, you see, if you have two A's, normally you would say they are the same because they are both equal to the flux of the magnetic field. Right? If I go round the loop once, any loop, and you use two versions of A, of the vector potential, the loop integrals must be the same. Because by Stokes' theorem, each of them is equal to the magnetic flux. And the magnetic flux is something physical. So the loop integral has to be the same. That is what you would do in undergraduate courses in EM. And that means delta A dr must be equal to 0. Right? That is the usual statement of the gauge degree of freedom. If you choose an A, I choose an A, the difference when integrated around a closed loop must be 0. That is your usual statement. But by using the fact that the two A's live in two different vector spaces, that is the relaxation we have introduced. All right? And the transformation between these two is a phase rotation. It's really changing the wave function by a phase. You find that the effect of this actually only comes about through here. Okay? Only comes about through here. And all you need is this is equal to 1, which is a slightly weaker condition than saying that the exponent is 0. And if you assume this, then 4 pi g is equal to that. You just shake things around. You find E times G is an integer times h bar over 2. Now, first of all, you check some units. The elementary unit of charge and the elementary unit of magnetic monopole in these units is just the unit of action. Okay? And the two multiplied together is just an integer unit of h bar over 2. Now, we know what the elementary unit of E is, right? 1.6 times 10 to the minus 19 coulombs. You know what h bar is. So this argument tells you that if monopoles exist, it must be some integer number of a fundamental unit, which you can calculate a priori. Cannot be any unit. Has to be a fundamental unit. And this is, of course, the same result as Dirac obtained, but using a much more complicated argument. Now, this argument, which was in one of the reference papers, Yang and then Wu and Yang, about 1976 or so, right, makes you think a little bit about the nature of the vector potential, namely what we have described. The vector potential need not be defined globally. It is defined only in private vector spaces with a consistency requirement. Once you accept this concept, which is actually quite general, and this is something I will talk about next time, the actual calculation is actually quite trivial. I mean, every step of the calculation is something that a second-year student, undergraduate, can do, right? The usual sort of thing by handling Stokes' theorem and so on. It's just that you are now careful in doing it separately for the northern cap and the southern cap. And you arrive at the condition for this quantization. Is that all right? I think I will stop here. Next time, I will do two things. One is I will generalize this idea and introduce the language of fiber bundles. That's just a language. And the only point is just in case some of you want to read mathematics textbooks or something, you know how the terms translate and why they do things like that and so on. You know, mathematics papers and books always have the problem that they are very rigorous, but they never tell you why they make those definitions. Okay? Why they ever dream of something so weird. And I hope at least to tell you why, not being very rigorous by leading from this example. The second, and I hope you will, I will not formally assign this, but there is a problem in the homework set about deriving this condition in a very simple way, where I lead you through step by step. Okay? No need to hand in, but do that before Monday. And I will also, quickly, and I will also take you through that problem. That's, in a sense, an even simpler calculation. That whole calculation, I did not mention A at all. I don't even talk about the vector potential. And will arrive at this condition. All right? And again, using techniques that even a first-year undergraduate should be able to handle. All right? Except the last part of that problem, where I pose a slightly tricky question. But getting that answer is actually very simple. All right, so let me stop here. Any questions? I believe we have only, not counting the makeup class, we have 2 more classes. Is that right? Monday, today's Friday, Monday and Wednesday. Next Friday is a makeup class. The exam time has been announced. I think, I don't know which day it is, but it's posted, right? Take a look. Why don't you post the exam time also on our website? All right, so also do that one more problem. Now, the other assignments for next Wednesday, I have already written out. Okay, we are a little bit behind, but that's okay, in terms of assignments. All right, so let's stop here. Any questions? Yeah. Question.
Professor, just now you said that there are 2 approaches towards the relationship between E and G. One is using A, and one you can simply ignore A. So what is the importance of A towards the magnetic monopoly?
No. I said that the solution I gave, which is the exercise, I did not mention A. But of course, you have to slip in quantum mechanics somehow, right? Otherwise, how will we ever get an H bar in the answer? All right? So you can say the deep question is how monopoles is consistent with quantum mechanics. So you somehow have to slip in a quantum condition. Okay? And the quantum condition we slipped in is that angular momentum is quantized in units of h bar, right? Or change of angular momentum can only be integral number of h bar, say from -1/2 to +1/2, or 0 to 1. Right? That is the only condition we use from quantum mechanics. And that is a bit of a trick. It is slightly less general. This is certainly more general. The idea is more fundamental, that you have A's defined in vector space, private vector spaces. That's an idea that can be generalized. But if you just want this result without that mathematical apparatus, that particular result, then there is a way of getting it by doing something simpler, by slipping in quantum mechanics in a slightly different way. Right. Okay, so let's continue on Monday.